Well, thanks to the organizer for inviting me and giving me this opportunity. And I'm sorry because I just arrived this morning and I have to go in a while, so it's a very short presence. For this I apologize. So this I'm going to talk about is a sort of overview of what we are doing and we did in with some system that span from nanoparticle to liposome to micelle system. We are we are physical chemists, and my specialty actually is basically synchrotron radiation and neutron scattering. So that are tools perfectly tuned and perfectly, almost among the most important tools for investigating the system you're using in your formulation. So this is a work that done by several people, but the most important people that contribute to this, what I'm going to show you today, is Deborah Berti, Costanza Montis, and Massimo Bonini, and former students that now are not anymore in my group, Silvia Nappini, which is at the synchrotron Elettra in Trieste, and Baldelli, that was in the UK and now is in the Polytechnic in Milan. Basically what we are doing, we are working with is soft matter, and in soft matter there's a sort of so-called soft matter triangle, and you can design the system that belongs to the soft matter, just drawing a sort of triangle like that and putting at the edges the most important system you can use, and in between they're system related. So in one corner you have a hard sphere, in the other one maybe surfactants, and then at the edge, the other edge is flexible polymer. What you have in between is something that you can use, you can mix, and I show you some system that belongs to this triangle, and they are mixing actually, mixtures obtained by mixing the edges of this triangle. Then of course you can go even inside, but if you go inside it's much more complicated. So the easiest system to investigate and to deal with are the systems that are at the edges and the borders, say, of the triangle. Inside is more complex stuff, and we start now understanding what's going on with proteins, which belongs to the core, say, of the system. So let's see, for example, a few examples like polymers, nanoparticle, and amplifier. Among these systems, I show you 3 examples. And the 3 examples that I'm going to show you is nanoparticle with polymers. Actually, it will be DNA or oligonucleotide. Then nanoparticle and liposome, or liposome and surface made of nanoparticle. I'm not going to talk about this. And the other one is polymers and amplifiers. Basically, is polymers, can be DNA, in this case, is lipoplexes, confined lipoplexes, and interaction with bilayer, lipid bilayer. So let's start with some example, and there's examples are taken for biomedical application, because you're interested in this field, and for drug and gene delivery, for example. So that's let's start. There's 2 main systems that we studied during the years. There's a magnetic nanoparticle And we like very much magnetic nanoparticle, much better than gold nanoparticle. That the first nanoparticle alloy we synthesized was in 1991, so a long time ago. But nanoparticle, magnetic nanoparticle are much more interesting in our view, because they're very easy to manipulate. We can trigger in a very easy way the cargo they might have, and then we can do the delivery and imaging at the same time. And we have a very good control in the spatial and, say, thermal response of the object. We can move inside the body just using a magnetic field. The other system I'm going to talk a little bit will be confinement of oligo like DNA or NA, RNA or other active principle. And there are several systems being used like lipoplexes or degradable polymers, dendrimers, but I'm going to talk to a different system we devise that are nucleolipoplexes. So there's several systems. Some of them have been already highlighted in the morning, and there's for example, liposomal system. Basically is a bilayer. You can add what you want on the surface. You can modify with PEG. You can modify with contrast agent. You can modify with antibody. You can modify, I mean, there's plenty target ligand. There's plenty of things you can do with these objects. The others, very similar, but they work in different physics in certain sense, are polymer, biodegradable polymer nanoparticle or responsive polymer, like what we saw in this morning. Another option is dendrimer, which are container in certain sense. They are disordered system. Of course, there's also gel, disordered gel, chemical gel, physical gel. There's a plethora of systems. But I'm going to talk about magnetic particles in vesicle, core shell magnetic nanoparticle, and nucleolipoplexes. So let's start from the first system. So for example, magnetoliposome. Magnetoliposome is an interesting system because you can form a liposome, and then you can use magnetic particle that you can put in different regions of the system to get different activities, say, different actions. These systems are quite interesting because are biocompatible. Their the composition and the size is quite flexible. You can design system as you wish, basically. You can modify and you can fully control the surface of this system, and you can encapsulate hydrophilic or hydrophobic molecules, and you can also control the permeability, the cell permeability, the liposome permeability by using, for example, nanoparticles. So if you want to devise a system like that one, first you have to start with nanoparticle. Now you can buy nanoparticle, but in some cases it's useful to synthesize on your own because you fully control the surface. So you start the synthesis of cobalt or cobalt ferrite nanoparticle. If you want to use particles just to show a proof of principle, is cobalt ferrite is much better. But if you want to use for say nanomedicine, is better maybe ferrite, or you can use also cobalt ferrite covered by gold. But anyway, ferrite is the most important particle you can use. So you synthesize and you have to control the size of particle. So you can start from the smallest can be 2-3 nanometer, but basically these systems are supraparamagnetic, meaning that the magnetism of this system change according to the size the responsive to magnetic, say, field change according to the size of particle. And this is a small particle. This is about 4 nanometers, and you can detect a very crystalline particle. Here there's the atom, the ferrite atoms distribution. Then you have this particle, but you don't know if this particle is the particle you want. And in principle, usually we don't do that, but in principle you have to do, and at least the first time you have to investigate the magnetic domain, and to investigate magnetic domain inside the particle, you have to use sunspot, means neutron polarized. It's a neutron polarization, and this is an experiment, is not common, but in this way you can get the distribution curve of the actual sides and the magnetic responsive sides of the nanoparticle. So this is just to show you that we have full control on this system. At this point you have particle, and you can decide to put particle in, for example, a container that can be liposome, and is what we did. Liposome actually are quite nice object to use with particle, because you can have a particle, and the particle can be small or large particle, can be coated, can be positively charged, can be neutral, can be negatively charged. So you just play by playing the synthetic, changing a little the synthetic procedure, and you can change for you can control the charge of the particle, you can control the size of the particle, you can control the clusterization of particle. It's worth to say that these magnetic particles usually are not a single particle. So magnetic particle, even the particle you use and you're supposed to be a single particle, are formed by a cluster of particles that are 4 or 8, because this depends on the residual magnetization. So this particle you can coat. If you coat with the layer like citrate, which is large enough, you can decrease the interaction among particles and stabilize the system, or you can coat with other system, like oleic acid. So in this case, at this point, you have a library of particles that you can use for specific application, and you can easily detect the particle in different ways. One of the most simple, say, method to detect, to see where the particles are located and where they are going or move around in the system, is by using confocal laser scanning microscopy and confocal fluorescence microscopy, and also light scattering, of course. So this is an example, an example of confocal microscopy, and the particles are in green, actually, are in green, so you can see the distribution of particles. Even here you see that there's not homogeneous distribution on the surface of a liposome, and here again. So then when you have this particle with this liposome with particle in specific region of the liposome, you can apply a magnetic field. Magnetic field you can apply in 2 ways. You can apply a static magnetic field, and in this case you move the particle around your system, or you can apply an alternating magnetic field. And if you apply an alternating magnetic field, you can apply in 2 different ways, because if you apply if you apply the magnetic field with high frequency magnetic field, basically you have hyperthermal heating effect that is operative due to nil relaxation. But if you work with low magnetic field, basically you just move the particle back and forth, and you disturb, say, in the sense, the system, and you can slowly thermally excite the the system. So what you get in one case at high magnetic field, high frequency magnetic field, you increase a lot and you don't have too much control on temperature, you have hyperthermal effect. If you use low frequency magnetic field, you just hit around the particle and you can release what's on the particle. You don't need to cook the cell in this case. And this is what we did actually. This is an example. So you have a liposome with magnetic particles that are inside the liposome. We apply a low magnetic field. The particle is still living. We don't disturb too much the particle, but we can open channels around and across the membrane to release the dye which is inside. And basically, this is the example. You apply the magnetic field here, and then after 10 minutes you lose fluorescence. This is a vesicle. This is the skin, say the bilayer of the vesicle, and inside there's fluorescence. So this is 0 minutes. This is 10 minutes of application of alternating magnetic field, and then in 20 minutes, basically, you lose what you have inside the liposome. But you see that the liposome is not broken. And basically, you can also easily detect the mechanism for the diffusion across the skin. So, the first part, the conclusion of this first part is nanoparticle can be controlled. The location inside the vesicle can be controlled, and can be controlled according to the charge and the surface functionalization of nanoparticle. You can release, you can control the release of what you have in your system, the cargo release, and by controlling the magnetic field, controlling the thermal behavior of the nanoparticle. Okay, this particle can be used also for releasing, for example, oligonucleotide. In this case, if we use the same triangle, we are working in the other edges, so polymers, and polymers in this case is DNA, single strand or double strand, and nanoparticle. And what we are going to do, show you, is that you have particles. These are ferrite nanoparticles, in this case are cobalt ferrite, and you cover by gold, and then you attach a single strand DNA. Then you have in solution a complementary sequence of this single strand that we call DNA staple. And then according to the temperature you have in solution, you can form clusters, and you can separate this cluster from the solution if you want, or keep in solution, because you have control on the clusterization, so you can control the, say, the number of particles you want in your cluster, and then you can apply a low frequency alternating magnetic field, and you increase temperature locally, the temperature, and you can control the temperature, and then when you reach the melting point of the DNA, you release the DNA sequence in the region where you are, where you want. So I go fast here because I want to show you something else. So you start from cobalt ferrite nanoparticle, you produce the nanoparticle and you characterize the nanoparticle, and you can characterize by using small angle X-ray scattering or dynamic light scattering or Z potential. These are classical methodology we use for nanoparticle. Then you coat the nanoparticle with gold, and here you can control the thickness if you want to increase or decrease the thickness depending on what you need. You can control the gold that you have on top of the particle. Then you can attach thiolated sequences, and in this case we work with a single strand 10 mer or 21 mer or 18 or 37. So this is what we call staple, and these are the sequence that can be complementary. So according to this, when you put in solution what you have, let's say if we work with the 37 mer single strain will be this. Then you have, this is what we call staple, and this is what will be on the single nanoparticle. So you have a particle, you have the sequence, and this is the staple. Of course, in the other part, you get another particle interacting with the staple. So what we get, we start from particle, you cover with gold, you cover with the single strand DNA. Thiolated single strand. You can even attach chemical. You characterize all this, and then in several ways. And then what you start forming the cluster. The clusterization is simple. You have particle in solution with the covered by DNA. You have to control the amount of DNA on the single particle, and then you add the solution, the staple, and you form the dimer or multimer, depending on depending on how big you want the cluster. And what's interesting in this clusterization is that the formation of cluster is not fully reversible. So you can destroy the cluster one time, the first cycle. So if you can use temperature to release the staple from the particle, and then when in principle what you expect is that you have a cluster, you increase temperature, you release the staple, and then the particle will be in solution. Then if you go below the melting temperature, you should reform the cluster. And this is not the case, because you can do this game just 1 or 2 times, because the first time you have the cluster, you increase the temperature, and you release, in effect, the staple, and you have particle in solution. But if you do this 2 or 3 times more, you have a thermal annealing of this cluster, and basically you form a very ordered crystal, so you anneal the crystal, and you cannot release anymore the staple. You have a very stable ordered crystal. So, but for our purposes, 1 time is more than enough. You don't need to reuse several times. And the proof that we have the release is, again, comes from giant unilamellar vesicles. You can use other system, but using giant unilamellar vesicle to see the release is quite easy. And you do exactly something similar to what we did before. I showed you before. Basically, what you have the vesicles. Inside you have the DNA and the nanoparticle and the staple. And here you have a dye which is, you can see the dye only, there's the dye that you have attached, the dye attached to DNA, is quenched upon the release of the staple, so the part of DNA that you want to release. And this is what happened. The green one is attenuation of the green fluorescence inside is the proof that we have released the DNA staple, that is the part that is labeled in this sense. So the last part of my talk is another system. These systems are, as you see, complementary among them. And then in this case, we are working in the other age. So we are working on polymers and amplifiers. And the typical system that in this area is what system used for gene delivery. And the system is very commonly used and very popular, are called lipoplexes. Lipoplexes usually are formed by polymers and so DNA, for example, or RNA, and cationic liposome. These systems are non-viral gene delivery agent, and they have some advantage over the viral, but still there's they're not quite good for delivering. There's some problem related to lipoplexes. There's some toxicity, and so we work for a long time in Well, these are, I don't know if I have time to show this or not, but depending on how, yes, you don't know how long I'm going to talk, so how much I Can I talk? Okay, so I go back. Okay, so these are lipoplexes. So, okay, this one possibility of delivery instead of lipoplexy, instead of using lipoplexy, is using directly DNA, DNA and modified form of DNA, single strand or even double strand. And we studied this in two different geometry. One geometry was in liposome or in flat geometry, in lamellar phase. This is quite useful because if you just want to show proof of principle, this is useful because you can use quartz microbalance and you have a full characterization of what's happening during the process, what we are studying. So, what we study is this, for example, is a derivatization of DNA. You have a sequence, actually this is the sequence, and the sequence is attached to an egg join here. So you have a DNA, you have an ethylene oxide link here, and then you have cholesterol derivative. You have and we call mono cholesterol derivative, and you can attach one single cholesterol derivative or two or three or four, and then you can use DNA like a surfactant. At this point, the DNA behaves like a surfactant. So we have a sort of cholesterol oligonucleotide. And what we study is this, how DNA behaves on the liposome. So first, you can couple DNA with the liposome, and then you can use liposome to carry around, say, the DNA. And then the problem is related to the amount of DNA you have to use for functionalization this liposome. And what we discover is actually something very interesting, because you have a transition according to the number of DNA you have per liposome, according to the surface area available for DNA. And this transition is according to a scaling law, well-known scaling law that was proposed by Pierre-Gilles Desgennes. And basically, when you reach the Flory radius, and then you change the conformation of DNA. So, in this stretched say, conformation, the DNA behaves indifferently from the other conformation. And actually, you can even see, because easily, actually, because if you do the hybridization kinetic, you can see that below the Flory radius, you have a decrease of the hybridization kinetics, and above you have an increase in the hybridization. And this is quite logical, because if you change the conformation, you change the steric hindrance basically of the chain. So this is a way where you can use to deliver DNA, and you can play chemically. For example, here you can put an ester link or whatever, and then you can use chemistry from cell to release the DNA, or you can use just the DNA and the cholesterol. But this is hydrolyzed. So this is a way where you use liposome and DNA. Okay, DNA solubilized, say, on liposome, the surface of liposome. Another way is still using polymers and amplifier, and this is different. This is nucleolipoplexes. That's what I was saying before. So instead of using lipoplexes, where you use charged molecule, cations, can be polycations or just cationic surfactant, which are toxic, you can use different molecules, and basically this we synthesize first. We were the first, I guess, or maybe the second, I don't remember. Synthesizing this phosphatidylcholine derivative. For example, you can produce a nucleoside derivative just cutting with the cleavage of the choline group. It is an enzymatic synthesis by phospholipase D, and you can use the phospholipase D to do the reverse of what you want to do, and then basically you cut the choline group and you attach the nucleoside that is in large excess in solution. And this way you get a phosphatidyl nucleoside. In this case is a phosphatidyl adenosine. Then what you have here, you have a surfactant with an intelligent head group that behave like nucleic acid. And you can use this to recognize sequence from nucleic acid. And this actually is what we did. So you can use the pure surfactant. Let's concentrate just on this one. It's the adenosine derivative. You can use the pure surfactant, but then you have some problem because these units stack one on the other one and are not so available for interacting with DNA. So the best thing is to dilute the adenosine, and you can dilute using different phospholipids. In this case we use the DOPE, which are quite common surfactant, phospholipid used in formulations, or POPC. If you do these are different surfactant. What you get is that in this case you get a inverse hexagonal structure, which is, say, the signature of the invert hexagonal structure comes from this neutron or small angle X-ray scattering. Or if you use a POPC, you get this one. You get a lamellar structure, which is actually this one. Okay, then is the problem is that at this point you have two different structures. One is a hexagonal, inverted hexagonal structure, so you have cylinder. The DNA is inside this cylinder, and in the lamellar structure, if you add DNA to this system, we will see later, the DNA goes in between the plane. So we can monitor basically the interaction with DNA with the nucleolipid, and what we see is that if you have in the bilayer a complementary lipids like nucleolipid POP adenosine, complementary of some base, in this case is a polyuridine, you see that you have absorption. If you use a common lipid, which is not complementary, so you use mixtures, for example, or POPC and POPG, where there's no complementary action, you see that you don't have any interaction, and this comes from coarse microbalance. So in this case, you use POP adenosine and, for example, POPC. In the other case, you can use even POP adenosine and POPG. But if you use these two without any recognition units, you don't have any interaction. At this point, what you want to have interaction between the lipids, the phospholipids, and in this case, nucleolipids, and the DNA, a sequence of DNA. And to do this, we can use the two different lipids I showed before, but you have to use calcium, because calcium promotes aggregation of DNA. And again, the calcium works with the mixtures of lipids when you have the complementary units, but doesn't work with the other one. So in this case, you really have the formation of the structure that I showed you before. Okay, now the problem is, we know, and we have the structure, and we know that one structure is hexagonal and the other one is lamellar. And then, actually, I'm telling you the story in different sequences, temporal sequence. And then we want to understand what's the difference in behavior in one structure and the other one. So what's the difference DNA in the lamellar and DNA in the hexagonal. At this point you can use confocal microscopy, and you can use in two different forms. Confocal microscopy you can use like just to image what you want, or as in this morning was highlighted in a very nice talk actually, you can use confocal fluorescence microscopy, which is the counterpart of light scattering or scattering. So you get interesting dynamic information, and from dynamics of DNA, in this case we follow DNA, you can understand what's going on in the system. So basically you can, if you want to use confocal microscopy, you have to use a dye somewhere. In this case, we can dye, you can label the phospholipids. In this case, you have Bodipi liposome with excitation of 496 and emission in 506, 530. Or you can stay in DNA. And then, in this case, what you follow the liposome, and you see that the liposome form complexes and precipitate, the particles are not dispersed. Or you can follow DNA, and you see that, again, you have, say, clusterization, because this forms the lamellar and the hexagonal system. What is nice if you map actually your system by using confocal microscopy, in this case fluorescence correlation spectroscopy, is that you can look at different regions of your system. Basically, you can look at the bilayer, or you can look inside the bilayer, and you can measure the diffusion of the molecules inside the system. And basically, if you study one of the systems, I show you, the two systems behave in different way, and you have several equations that you can use, but the most important is this, which is related to one-dimensional diffusion inside the object, or two-dimensional diffusion inside the object. For example, a DNA in a lamellar structure should diffuse as a 2D. So you should follow this law, but if you have DNA in a cylinder, like in the hexagonal structure, you should follow one confined diffusion. We will see that is not so true, because it's more complicated. So in 2D, you have indeed, in this system, you have a 2D diffusion, is a pure diffusion, which is a 2D. In this system, you have 1D diffusion, but it's not a pure diffusion, because these systems are wrapped with this layer, and in this layer, if you have some DNA around, not fully, not all inside, say, the cylinder, you have a contribution. So what you get anomalous. What we call anomalous is not possible. So you say, I could talk as a wish, and now you say a minute. Okay. So in this case, you have the contribution between these two diffusions, 5 minutes. Why we did this? Because if you use for transfection these two systems, actually, you see that one system, the hexagonal one, the inverted hexagonal structure, can say transfect, and in this case, what is transfect is the GFP. And in this case, you have no transfection. So must be, and this is important, there's a relation between the transfection capacity and the structure, local structure of the soft system you use. So it's not only a problem of how you put your system or how you devise the system. It depends on the structure that is not formed inside the system. And if you use the nucleolipoplexes, you get a little less transfection capacity in this case, but there's no toxicity compared, for example, to lipofectamine. Now we are in the position of understanding where the DNA is in the system. So since I have 5 minutes, I go a little fast. And what you do is this. First, you can label what? You can label the lipids, you can label the DNA, and you can mix the system in certain ways. So in this case, for example, you can see just the mixtures of DNA interacting with liposome. So in one case, you label just the liposome, then you add the labeled DNA, and what you see is that here you see the yellow, and the yellow means that you have the mixing of the system. In this case, where you're supposed not to have any transfection, any interaction, you see the separate system. At this point, you can even, if you want, detect the distance, the average distance by using FRET between DNA in lipoplexes, and this is something that we did. This is where you have the 2 chromophores in the system. And more interesting, you can have an idea of the structure that should be formed to get the delivery on the surface of the, in this case, bilayer. Okay, see, these are the 2 structures we have. During the transfection, you have the formation of this this channel in certain sense. But in this case, this channel allows the penetration and transfection of DNA. In this case, DNA remains in the lamellar phase. And we can measure the DNA that is transfected inside this giant vesicle. And this is a simple experiment. So you have double-strand DNA, in this case is a 50 mer, and is fluorescently labeled. Actually, this is a normal microscope. So you can measure, you can form the liposome, giant liposome or smaller liposome. Then you add the DNA outside, the complex outside, and then you measure the DNA, the fluorescence coming from the DNA inside the vesicle and outside the vesicle, and you need the calibration curve. And what you see that you have inside, you have DNA and you have transfection, and the transfection comes only with the system which is an hexagonal, inverted hexagonal structure. So I'm over. And then the conclusion are that you have to know the overall structure of the system you use and how the system relaxes. And then at macroscopical level, you use a scattering technique to detect the system. And you can use confocal microscopy easily, and fluorescence correlation spectroscopy, which is also quite easy technique to use to investigate the local dynamics. And in this way, you have a better, idea on how principle can be transferred across, in this case, our model system, but you can use the same methodology for real systems, even if are more complex. So 5 minutes, you say, thanks a lot for, and
so before opening the discussion, I would like to ask you a very brief question, just a